Let's do an overview from systemsarchitect.io on event-driven architecture in cloud systems design. Subscribe to the channel and like this video for more great tips. Event-driven architecture is a cloud design pattern in the domain of cloud application integration. It sits beside the request-response model most services start out with. Instead of one service calling another directly, one emits an event that other services react to. An event-driven architecture, or EDA, triggers actions when something notable happens. One component publishes a fact, and other components react to it asynchronously. A broker sits between the two sides and decouples them. Some event brokers include Kafka, AWS Event Bridge, Apache Pulsar, Confluent, Google PubSub, and more. An event is a small record that something happened. The publisher does not know or care who reacts to it. That indirection is what separates asynchronous messaging from a direct API call. Why does any of that matter to you? Knowing this lets you drain a traffic spike into a queue instead of dropping it. It also lets you add new behavior without redeploying the service that emits the data. Every event system has three roles worth naming. Event producers emit facts, event consumers react to them, and an event broker sits between. That broker is also called an event bus or a message broker, depending on the vendor. Amazon Event Bridge, Azure Event Grid, and Google Cloud PubSub all play this role. Self-managed brokers such as RabbitMQ and Apache KAHF-QK do the same job. The broker is what gives you loose coupling via events. Neither side holds a reference to the other. The publish-subscribe pattern is the default distribution model in event systems. One published event reaches every subscriber that registered interest in it. That is a fan-out pattern. A single order event reaches billing, shipping, and analytics at once. Fan-in is the mirror image, where many producers feed one consumer or one queue. Amazon SNS fanning out to several SQS is the classic implementation. Azure Service Bus topics and Google Cloud PubSub subscriptions give you the same shape. Event streaming keeps events in an ordered, durable event log instead of deleting them on delivery. Apache KAHF popularized this design, and Amazon Kinesis and Azure Event Hubs follow it. Consumers track their own position in the log rather than acknowledging one message at a time. So what does that unlock? That gives you Event Replay, where a brand new service reads the history from the beginning. Most brokers promise at least once delivery, which means duplicates are normal rather than exceptional. Exactly once delivery exists in narrow cases, such as KAHF-QU2 transactions. But it costs throughput and complexity. The practical answer is idempotency in event processing, so handling the same event twice changes nothing. When a message keeps failing, the broker moves it to a dead letter queue, or DLQ, alarm on dead letter queue depth, because that is where lost business logic quietly piles up. An event schema is the contract between producers and consumers. So why bother writing one down? Without one, a renamed field breaks a downstream service you have never met. A schema registry stores those definitions and enforces compatibility rules before a producer can publish. Confluent Schema Registry, the AWS Glue Schema Registry, and Azure Schema Registry all serve that purpose. The CloudEvents specification is a vendor-neutral format for the envelope around your payload. It standardizes fields like source, type, and ID, so tooling works across providers. Coordinating one business process across services happens in two ways. Choreography lets each service react to events on its own, with no central controller. Orchestration puts one component in charge of invoking each step in order. AWS Step Functions, Azure Durable Functions, and Google Cloud Workflows are orchestrators. The Saga pattern handles long-running transactions by pairing each step with a compensating action. A failed payment triggers an inventory release, since there is no rollback across separate databases. Learn more at systemsarchitect.io. Like and subscribe to the channel and follow the playlist. Event sourcing stores the sequence of events as the system of record. Current state becomes a projection you rebuild by replaying that sequence. CQRS, or Command Query Responsibility Segregation, splits the write model from the read model. Writes append events, while reads hit denormalized views tuned for each query. Complex Event Processing, or CEP, looks for patterns across many events in a moving time window. Fraud detection and equipment alerting use it to spot 3 failures inside 5 minutes. Reliability improves because a queue absorbs load your consumers cannot take yet. A downstream outage delays the work instead of failing the customer's request. What about scale? Scalability improves because each consumer scales on its own backlog depth. Cost tracks usage closely when consumers are serverless functions billed per invocation. Extensibility is the benefit teams feel most, since adding a subscriber needs no upstream change. Skip events when the caller needs an answer right now. Checking a password or quoting a price wants synchronous request response, not a queue. Eventual consistency is the price of this style, and some domains cannot pay it. A 3-service application gains a broker to operate and loses its simple stack trace. Start with direct calls and introduce a broker where you actually feel coupling or back pressure. Event-driven architecture connects producers and consumers through a broker, so components react to facts asynchronously instead of calling each other directly. The patterns that make it work are publish, subscribe, fan out, durable event logs with replay, and idempotent consumers backed by dead letter queues. Version schemas and sagas carry the multi-step work. Reach for it when you need loose coupling and elastic scale. Stay with synchronous calls when the caller cannot tolerate eventual consistency. Thanks for checking this out. Hope you learned something. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io.